So we spent a decent amount of time really chatting a lot about tungsten today and this particular milestone and moment in time. What I really wanted to do was start our AMA today by chatting a little bit about some of the earlier days for the DFINITY project and some of the work that you did in your past. So from a first question, perhaps you could share a little bit with all of the community members watching around where the inspiration for the Internet Computer came from.
I've been a long-time nerd, and I started messing around with distributed systems and cryptography back in the late 90s. And, before I got into crypto proper around 2013, I'd created a computer game, an MMO, that scaled to millions of users. And I used a decentralized database called Cassandra, and also created scale-out, horizontally scalable application server to support the interactivity on the platform. And I actually had an algorithm called a weight chain algorithm that enabled some stuff on Cassandra, another thing called Starburst that enabled the application server to work. So, I was already programmed to think in terms of using decentralization to scale out. And then I came across, Bitcoin was on the edge of my sort of consciousness, and I'd read, the Wade Dye's B-Money proposal back in, 1999 or something. Didn't really understand it, but, Bitcoin went through its April pump in 2013 and got my attention. I'm like, wow, man, this is actually working. You can use a fully decentralized network to share a consistent state. It's the world's first stateful decentralized network. And I was absolutely enthralled, as many people were when they first read the Bitcoin white paper. And then by the end of 2013, I was getting frustrated. I was thinking, well, how can I create an altcoin that could be used to support a virtual currency for the games industry? And clearly, you needed much faster finality and scalability and so on. And so I spent much of 2014 exploring traditional Byzantine fault-tolerant consensus protocols, particularly leader-free asynchronous protocols, and proposed this thing called Pebble. And then, of course, the Ethereum project came into being, and that demonstrated something even more interesting, this idea of a blockchain computer. And for me, I saw things, I saw a bigger picture than just smart contracts, and I thought, well, wow, potentially all of humanity's software and services could run off a fast, scalable blockchain computer. And so I started thinking about how that could be done, and I started making early proposals under the DFINITY tag in 2015.
One of the things I also wanted to chat a little bit about is, in your words, where do you believe the project is currently at? We speak a lot around where we would really love to see this project go. And sometimes it might be missed that, this is really a very grand vision. And in some of cases, it might take us years, maybe even decades to accomplish some of these things. So we'd love to kind of get your thoughts on where do you believe the project is at today?
Well, to be clear, over time, there's been a lot of pressure just to launch something and have a internet computer chain. But we've stuck to our guns and said we will only launch something that clearly is the internet computer. So that means we have to be able to support the high levels of performance necessary to run an internet service from what is a blockchain computer, and it has to be able to scale out. And the reason for that is if you can't scale out very quickly, you run out of capacity and everything stops working. And we saw that, for example, with CryptoKitties on Ethereum. Once the capacity was used up, finality went up into the hours. And so, that's why we're called DFINITY. Decentralized infinity means that we need a blockchain computer that can scale out to any capacity as necessary and also, of course, provides the performance. So in order to deliver this, you need to do a lot of technical work. And it's not just engineering. There's also a lot of research and science behind the Internet Computer Project that you don't see when you're just playing with the SDK. And we're going to be revealing more of that progressively. I think a lot of people may already be aware of the original sort of threshold relay and probabilistic slot consensus proposals. And we're still using something like that, although it's more advanced and, as you would imagine, has benefited from several years' work. We've got novel cryptography, all kinds of things inside the project. Now, there's a big difference as well between theory and implementation. So, we proposed threshold relay some time ago. It works very well. However, in order to actually use that within a decentralized network, you need ways of running something called a DKG, or distributed key generation, or in this case, something that might better be called a decentralized key generation protocol to set up the underlying key shares and things like that. And that is extraordinarily complex and so on. So we had to build a different kind of blockchain organization to have any chance of delivering the Internet Computer Vision. And truth be told, we probably underestimated the difficulty initially. But we kept at it. Yeah, we did. We kept at it relentlessly, though, and we've built out this amazing organization. We've got several research centers, a very large team, very large multidisciplinary team. We've got some absolutely outstanding people across everything, all kinds of disciplines, but yeah, of course, also within research and engineering. And I'd say that the organization really began to hit its stride last summer, and we've become a kind of powerhouse. And now we're making amazing progress. So we created these 5 public milestones to launch. The first was copper, and we hit that in November last year. Second was bronze. We hit that at the World Economic Forum in Davos, January this year. This is the third, tungsten, where we're sort of opening up the internet computer incubation to developers, and actually behind the scenes there's a whole load more features that have gone into the network. Some of them not quite there yet, like the ability to fork canisters. The next 2 are sodium, which adds network nervous system governance, autonomy and economics and things like that. And the last one, of course, is mercury. So we've hit the first 3 milestones on time, and I'm hopeful that we're going to hit these 2 following milestones on time too.
So following up on the idea that there is going to be this discrepancy sometimes between theory and implementation, I want to follow up with a quick question that was actually asked by one of the community members during the presentations today. And this one comes from Asafra and Vermeji. And the question was, what do you expect are going to be some of the most exciting / critical next steps in the roadmap? And I know you just spoke of a couple of them, but in your own opinion, what do you think might be some of the most exciting / critical steps that lie ahead for us?
So I think, the community as a whole will be very excited by the network nervous system. It's one of those things that people have often sort of poo-pooed over the years and said it's impossible. And I think people will be very excited to see it actually working. And I think it'll be entertaining too, because everyone will be wondering how this algorithmic governance system is going to churn out decisions on proposals that are submitted. So I think that's going to be fun for everyone, myself included, to watch and play with. Separately, behind the scenes, there's still a lot of interesting technical work being done. So for example, at the moment, the replicas don't make use of the concurrency that's possible when you're running function calls on canisters. And the ultimate evolution of that, where we're heading, is something called deterministic time slicing. And I'm keen to see that done so we can really fully use all of the cores that are on the node machines in the Gen 1 spec, or that are already deployed. And there's also some really exciting new cryptography. So as hopefully people got a sense of, the overall network is controlled by the network nervous system. And the network nervous system actually runs on a dedicated subnet that's extra large. And the network nervous system has a public key, essentially. It's the public key of the subnetwork. Now here's where it gets really cool. The subnetwork, the composition of the subnetwork in terms of what nodes make it up, is controlled through this thing called the registry, which is controlled by the network nervous system. So the architecture of the overall network is dictated by this thing called the registry, and the registry is updated by the network nervous system. And so the network nervous system controls the composition of its own subnetwork, i.e. the network nervous system controls what nodes in the overall internet computer network it's running on. So first of all, the network nervous system, if you like, is able to sort of move around cyberspace and control in a Byzantine fault-tolerant way, using consensus, and control what nodes it's running on. So that's pretty fucking cool. And on top of that, the network nervous system actually has a public key, which is constant for all time. And it's able to maintain this public key even as nodes are swapped in and out of its subnetwork. And that means, that's enabled some very large advances. So, for example, if you were a user app, right? Traditionally to validate a blockchain, you have to download all the blocks and so on. That would be impossible with the internet computer because there's too much data and too many transactions. On the internet computer network, all you need to know is the public key of the network nervous system. It's 32 bytes, 256 bits, right? And you can connect to any node in the overall network, and you can ask questions like, I want to interact with this canister, and it can tell you, well, please go and talk to these nodes which are responsible for replicating it. But when it tells you that, it'll give you a little bit of the registry that's been signed by the network nervous system. So as long as you know the 32-byte public key of the network nervous system, you're able to validate that information that's been given to you, right? And of course, that information also gives you the public key of the subnetwork that's hosting the canister you're wanting to talk to. So now you can validate interactions with the subnetwork. So, that's an example of a big advance. Rather than downloading a whole blockchain, you only need 32 bytes, the 32-byte public key of the network nervous system. But there's even more clever stuff in that you can, that whole system will integrate with the DKG, and if a subnetwork loses for some bizarre reason a vast number of replica nodes, in principle you can rebuild the entire thing. The network nervous system can rebuild the entire subnetwork from a single remaining node, including all the cryptographic key shares, and get the whole thing up and running again. So, people won't see this. If you're a developer, the subnets are transparent to you, right? You just upload your canister to the internet computer, and your canister has an ID, and if your canister wants to call another canister's functions, it only needs to know the identity of the other canister and the function signature. The actual structure of the network's transparent. But behind the scenes, there's a whole lot of really clever stuff going on. And so as we go through this year, we're going to be publishing a lot of this, as well as sharing a lot of the, opening a lot of the code.
I did want to kind of mention, so as we've kind of gone through the years at this point, working on the internet computer, there have of course been some project delays. And I would love to kind of get your thoughts, kind of looking back at the time that we've spent getting to this point. What has been surprisingly difficult, as far as implementing? And I think it would be good to give the community a sense of that.
Nobody should underestimate the challenges, the technical challenges involved in building something like the internet computer. It's a very non-trivial project. And I just talked about some of the custom cryptography involved, and we've got some of the world's best cryptographers, and you really do need, you can't really sort of crowdsource that kind of expertise. And so you need to build a sort of organization that's capable of bringing those kind of people in and then coordinating them. And that's very non-trivial too. So, I think back in 2017, I said that we want to build a NASA for decentralization. And we've been completely true to our word. At the time, there were all these kind of funny memes flying, around, like, rocket ships with the DFINITY logo on the side and so on. Everyone thought it was very funny. But we've been true to our word. I think the bit I certainly underestimated was how long and how difficult it would be to build a NASA for decentralization, like to build out the infrastructure, to create the research centers, to hire people, to create the sub-teams necessary to build out all these different pieces, and there's a lot of them. And then find ways to coordinate those teams. It's challenging, and and to hire the necessary people. So, we've done that, and I think about a year ago we really began to hit our stride as an organization, and we've become this powerhouse, and we're continuing to expand and get better and better all the time. But it took longer to get to that point than I'd have liked. Whether it could have been done quicker, I don't know.
Got it. So the next question I want to share comes from Sayuri Inada, and she wants, or he, pardon me, or she, wants to know, what is the data center concentration risk in your view? And I would love to kind of get your thoughts on that, because as we spoke a little bit about the data center model, this for some people might, vary widely compared to what they may have seen before coming out of other projects like the Ethereum Foundation.
So it's a really good question. And I've been involved in blockchain for quite some years, and I'm absolutely obsessed with the underlying science. And we've seen, for example, the problems of centralization in proof of work systems. And, there's even been cases, I think, where, Bitcoin's mining pools have acquired over 51% of the hashing power. There's also another problem in those kind of environments, is that in that you never really know who owns the hashing power. For all you know, it could all be owned by a single party. And that means, if that's the case, the Byzantine fault-tolerant protocol math doesn't work. The same issues with centralization can occur within proof-of-stake networks. So the design of ICP firstly rewards node machines rather than stake. Like every single node machine that's not statistically deviating, that's how we detect faulty behavior, or maybe someone running a node that doesn't meet the hardware spec. Every single node machine that's not statistically deviating gets a fixed reward every month, right? So you increase your revenues by running more nodes. Now, the way we get security, the way we create this tamper-proof and the tamper-proof and unstoppable properties of the environment are through composing subnets by selecting nodes from independent data centers, right? It's just not possible for a subnet to have more than one data center, and that's by design. So, it's certainly true that there are some advantages to scale, in the sense that the more nodes you run, the more revenues you make. But it's not like proof of work, where the ability to generate profits depends very heavily on the cost of electricity. So, in practice, the internet computer network will be far more amenable to professional amateurs than a proof of work network. And the ICP protocol, through its governance system, the network nervous system, inducts data centers, right? So data centers come into the network with a data center ID, and they have to join nodes using that data center ID. And this allows the network nervous system to compose subnets from nodes from independent data centers, which gives you guaranteed decentralization and allows the Byzantine fault-tolerant protocols to work much more effectively and provide far higher levels of, security and liveness than would otherwise be possible.
And this one comes from a Matt Quinn, and it kind of starts diving into a few more questions on the development experience for people who are utilizing the internet computer. And Matt's question was, what can you share at this stage around canister storage cost? I really think ultimately it's going to come down to, for a lot of people, how expensive is it going to be to utilize the internet computer?
So it's a good question. I can't give you a specific answer, because economics are coming in with sodium, which is the next milestone. So hopefully you'll have a specific answer at the end of Q3. But what I can say is that the internet computer is designed to be efficient enough and inexpensive enough to use to support hyperscale internet services, things like social media, right? Which is why we're demonstrating CAN-CAN. It is true that the internet computer uses replication for the purposes of Byzantine fault tolerance, and therefore you might assume that the cost of memory will be greater than a traditional project would experience when they're using like Amazon Web Services, content distribution network, and so on. What I'll say is this: We have got some special kinds of subnet coming along. Probably they'll arrive after Mercury, that enable sort of allow you to create canisters that have very low cost memory, right? For the purposes of storing, massive amounts of data cheaply. But separately to that, I don't think there's going to be a problem. I'll tell you why. If you actually look at the way the legacy stack maintains data, there's replication everywhere already. First of all, you've got your database, and then, there's the data file, the index file, then you've got the backup snapshots, the log file, and, then you're using memcached because you've got to speed it all up, and then you're almost certainly using a content distribution network to make sure copies of your data exist on the edge of the network. And when you really drill down to it, I don't think that the internet computer uses much more replication at all. But we just embrace replication, which is much more intelligent, to deliver a tamper-proof environment that's unstoppable. There's also a native edge architecture, so you don't need a content distribution network. And in fact, we can actually dynamically generate content for you on the edge, in many situations providing far better performance than a traditional internet service will be able to achieve using a hyperscale data center and a content distribution network.
So I'm going to ask one of, I think, the community's most frequently asked questions, and I think it's always worth us spending some time to chat about this and revisit it as we kind of meet our different milestones along the way. And this one is going to come from FC22. And the question is DFINITY going to become fully open sourced once mainnet goes live? And I would love to kind of get your thoughts around not only just the answer to that question of whether or not we will be open sourcing more portions of the internet computer once we kind of get to that public network launch. But I'd also like to get some of your thoughts on, whether or not you feel the strategy of not open sourcing all of our content earlier on has been beneficial.
Yeah, good. All good questions. So first of all of the code that implements the ICP protocol will be in the public domain by Mercury. And it has to be in the public domain because otherwise how could anyone verify that it correctly implements the ICP protocol? In addition to that, before we launch, we're going to push vast amounts of technical content out into the public domain. I think I mentioned before that internet computer projects different to most blockchain computer projects in the sense that there's a hell of a lot more novel technical work going on behind the scenes. It's more like a blockchain with 100 white papers kind of thing. We're going to start pushing all of that stuff live, and I think people are going to be really enthralled to see some of the stuff that we've come up with. With respect to open source, we've already started pushing, I think, a lot of the SDK and the canister environment and Motoko implementation live. I think it's using Apache 2 with the LLVM exception. I will say, though, that I'm also interested in new variations on open source, which I sort of call collaborative open source, where you can specify specific projects that can use it, right, to encourage contributions back. So, for example, we might say, well, look, we love the Ethereum project. Hey, we will mark this code as usable by the Ethereum project, right? So everyone will have access to it, but it might limit who can use it. And the reason for that, and this sort of impacts on the other part of your question, is why we don't release everything. Part of the reason we don't release everything is we want the ability to make our mistakes in private, and we still sometimes go down one path and back up and go down another path and things like that. And it's only now that we've really stabilized the way we're doing things. But the other piece is that we don't want people just ripping off the code and the systems and just using it to create some ICO ripoff. And there is a sort of tendency sometimes in the blockchain industry to just see this sort of buffet of techniques that are available and sort of cobble them together and then just push something live and say, hey, it's this amazing new thing. And we don't want to feed into that. We want people to develop their own original ways of doing things, and for the internet computer to be its own original thing too. So I think there have been a number of reasons why we've operated in stealth, and I think that period's coming to an end, and people are going to see all this really cool stuff that we've been working on, and we're moving into a phase where we're going to be much more open in the future.
Very exciting. So I want to switch gears to chat a little bit more about just the timing of all of the work that's been going into the DFINITY Foundation and the Internet Computer more broadly. And I would just love to get your thoughts. And I know you speak to this quite often, but for some of the people who are joining us today, perhaps for the first time, just why now? Why is now a great time to see something like the Internet Computer brought to market?
For those of you who are a bit older like me, and when remember the 1990s, the internet's lost its mojo. It's dominated by big tech. The stack sucks in a way that takes a lot of the joy out of software development. And if you want to create a new internet service, typically you have to build on the APIs of big tech, which is like building on big, on shifting sands. So, the internet's ripe for a change. It's not just us saying that. And we want to enable this shift where the internet becomes connectivity plus shared computer, and everyone just builds on the public internet. And when that happens, the internet's going to be transformed because the Internet Computer Platform enables, for example, autonomous open internet services to create non-revocable APIs, which enables something called service composability, so that the whole ecosystem can be built out much more dynamically and collaboratively, enabling more innovation and much greater network effects, which are needed to beat out these monopolistic incumbents who've hijacked everyone's user data and relationships. So that's going to be very exciting, and it's going to enable this sort of new wave of entrepreneurialism and growth and exciting times. And it's also going to change the model, because today, look at LinkedIn. LinkedIn started off espousing the programmable web, right? They shared APIs that allowed other services to incorporate professional profiles from its network into their own services. And that was one of the ways they grew. Like, lots of startups would forward their users to LinkedIn because they thought they could use LinkedIn as a kind of database for professional profiles. Of course, eventually, LinkedIn had everyone's professional profiles. Microsoft bought them, and they decided, well, look, it's much better to be a monopoly. And they revoked everyone's API access. And thousands of startups are absolutely poleaxed by this. And now LinkedIn continues, in the role of a monopoly with its hijacked data, and it just sort of grants a few select services in the big tech oligopoly access to them, like Salesforce. So, innovation, of course, has stopped on LinkedIn, as it has on many other platforms. I mean, how often do you see a change in Google Search, Gmail, eBay? All of these services just stop innovating once they become monopolists. With the Internet Computer paradigm, it's much easier to create new services because you can build on existing data and relationships. And that's, sharing the user data and relationships that are in your service is one of the ways you're going to succeed, by getting these, leveraging these mutualized network effects and getting people building on top of you, so you can collaboratively build out your ecosystem through service composability. So that's how you succeed and how you beat out monopolistic incumbents. But, there's a sort of pact that's made with the platform there, right? Once you've created permanent APIs that can't be revoked, if you're, say, linked up, and you're the new open social network for professional profiles, and then at some point in the future, your tokenized governance system decides to turn sort of monopolistic, right? It can't really do it because it can't switch off the APIs. It can't even degrade the functionality behind them because the network nervous system will reverse it, which is another topic of conversation.
Maybe we save that for
yeah. So essentially, you've got to keep on innovating, right? Because if you don't keep on innovating, someone's going to create, open linked up too, and just use the professional profiles that you've already collected through those permanent APIs that you created in order to grow yourself. So it, redefines how the ecosystem works, which I think will be better for everyone. It'll be a huge democratizing force, and it's going to enable much, much higher levels of innovation on the internet.
Thank you again for those answers, Dalman. To close things out, I have one last question for you, and it's essentially, what would you like to see the people who are watching this video to do next? Some of them may be developers, some of them may be DFINITY enthusiasts, community members of different audience types all over the world. In your opinion, kind of what is the next step that they should take to really help us in our journey in trying to reboot the internet?
Well, understand the paradigm, understand the power of it, understand how to leverage that. And there are lots of different ways, right? The internet computer is going to make it much easier to create scalable internet services. But you can also use it for DeFi, enterprise systems, pan-industry systems, just simple websites and so on. But if you're an entrepreneur and you want to create the next wave of open internet services, understand how you can use the paradigm to compete and become successful. So, it could be token economics. You might create an open Uber and give out governance tokens in from your tokenized governance system to early riders and drivers. Understand how you can use the paradigm, and then go and do it. We've got well, not us, but there's an associated venture capital fund called Beacon that focuses on the internet computer projects, but it also invests in DeFi. Actually, its first investment was in Compound, which has done very well. But generally speaking, there's a huge amount of capital sitting on the sidelines, ready to go into projects that are building the open internet. I mean, everyone knows that the current internet is a busted flush. Everyone knows it's controlled by big tech. Everyone's bored of it. Everyone's frustrated that opportunity is being sort of snuffed out by them. And everyone wants to see the open internet succeed. And there's a vast amount of capital. Like when you get a monopolistic system, the thing to remember is that there's always going to be a lot of losers. When you're talking about tech, there's a lot of highly motivated, smart losers, entrepreneurs and investors. And the internet computer is designed to create a way past all of this. And there's an awful lot of VCs out there that will invest in the best projects that assemble really good teams and prototypes and things like that. So, we're looking to support people doing that.
Well, thank you so much, Dominic. This has been wonderful, and we had a really great time today watching all the different presentations, and I'm really excited to start seeing what some of the developers out in the community start doing as it relates to the Tungsten release of the Internet computer.
Thanks, Mike, and super thanks to everyone attending.